Good afternoon, everyone. My name is Nabunya Desire Christine, and I'm very excited to present to you our AI project, which is the GAN Augmented Multimodal AI for health, meal preparation, and local food sovereignty. In simple terms, we have built an intelligent kitchen assistant which is designed specifically for the Ugandan people and communities, which aims to make healthy eating easier and more accessible to everyone. So, at the heart of our project, we have several key AI concepts. Number one is the multimodality, which uses multiple data types, which include recipe, that's text, then videos, including the cooking steps, and the images show the ingredients. So, all of them together, we were able to, they helped us to get a variety of different outcomes. The second concept is GAN-based data augmentation. One of the biggest challenges in Africa is a scarcity of local data. So to solve this, we use the generative adversarial networks. And a network has two parts. As you can see here, this is the generator and the discriminator. The generator tries to tell the difference between fake and real by training them against each other. Then the generator becomes incredibly good at creating the realistic images from here, allowing us to expand our very small data set and building more accurate models, as we shall see. So thirdly, we use computer vision, and just as our eyes and the brain work together to identify an object, our system uses a camera sensor as a vision transformer to recognize local Ugandan ingredients in real time. Fourth, we integrate a large language model. These are advanced tools, AI systems that can understand generated human-like text. And in our project, LLM acts as a conversational brain for our assistant, which allows users to ask questions naturally. Finally, our most important key concept that we used is the knowledge graph. So this is a central brain of our system. It is highly organized database which maps complex relationships between Ugandan recipes, their ingredients and nutrients that they contain, and their impact on the health outcomes. So this graph is what allows us, our system, to provide a truly intelligent and personalized healthy meal recommendation. Putting all of this together, we get a unified digital kitchen assistant for resource constraint settings. Resource constraint settings, these are people that are not able to access the internet at any time they would like. So our system can assist them very well. What problem are we actually solving? We identified two sets of challenges. One is the domain application problem, where existing apps on the internet and many platforms are culturally biased to Western food, recipes, and cooking methods. And very many Ugandan communities, especially people that are in the cities, struggle a lot to find planned and personalized eating healthy meals according to the ingredients that are available in their locality. Then, this altogether leads to reliance on imported and processed foods. Then, from the computational problem, the primary challenge is a severe data scarcity for the local Ugandan foods. This is compounded by the complexity of integrating multiple AI models such as vision, language, and graphs, as we are going to see, and then we deploy them all together on a low power mobile device for online use for everyone to access. Based on our problems as earlier discussed, our research objectives are very clear. So we aim to first build the multimodal AI assistant by combining the computer vision and the nutrition knowledge graph. Secondly, we implement the GANs to augment our limited image and text datasets. Sadly, we then model our real-time CV system for ingredient recognition, and lastly, we then deploy our system on an efficient and offline fast mobile application. Then our contributions are the direct outputs of these objectives, which was successfully built on our multimodal assistant, implemented by the GAN augmented pipeline, modeled by the CV system, and deployed as an offline application. Our first major task was to build a dataset from scratch. We then started with a foundational book, a cookbook of Uganda traditional foods from the internet, and manually digitalized the recipes. To overcome the lack of images, we scrapped and generated over 1,000 images from over 68 PDFs from the internet, resulting in a final clean dataset of 978 images across 40 food classes and 162 unique JSON recipe files. Our exploratory data analysis shows a fairly balanced class distribution, though some classes have more uh, food items than others. The data is clean with no corrupt images and is set for data training. This diagram shows our complete system architecture, and let us go through it. On my left, we have a user input, which can be either a text query, a voice command, or a live image from the camera. Then this input goes to the AI model. The AI model, which includes the CV module powered by VIT transformer, identifies the ingredient images. Then the LLM model, which has been fine-tuned on our dataset, processes the text or the voice commands queries to understand what the user would love to have that particular day. Then the combined context here, the identifying ingredients and the user's likes, what the user wants, is then fed into the knowledge graph, which then performs reasoning to find a personalized recipe that matches the user's health profile. Now let us dive into one of the models that we built. The first one is a relational graph convolutional network, or you can call it an RGCN for our knowledge graph. So what does this architecture that we see here mean? So the architecture is an encoder decoder. The RGCN encoder takes our graph data through two convolutional layers, which are rich in numerical vector or embeddings, as you can see just below each and every layer. The key innovation is that it uses a unique practical transformation for each type of relationship, allowing it to understand the context of the connections. Then going on forward to the formula, mathematically this encoder's formula, as you can see up here, shows that the node's new embeddings HI, which is a combination of messages from its neighboring vectors hj, and when each of them is transformed by a relation specific weight wr from this formula above. Then the dist malt decoder is another way, which uses this final embeddings, the final place, which uses the final which uses the final embeddings to predict the new links in the RGCN. It then formulates and calculates a score, which is called a possibility score, which is then gives us a product of three wise vectors. And lastly, the model will learn by adjusting its weight to give a higher score than the false one. So it will be learning in that process. And this process is called a BPR loss function. As we can see, it is calculated at the end of the slide, learning objective, BPR loss. The architecture that we see here is of our second fine-tuned LLM, which is a neural network. This neural network is built on the top of pre-trained embeddings, and this is how it works. So when a user asks a question in text, it is first tokenized and converted into numerical indices. Then it goes on to the embedding layer. This embedding layer transforms these indices into vectors, the dense word vectors. And these vectors are later on flattened and passed through a series of hidden layers. Here we used three hidden layers, and each hidden layer consists of a linear transformation, a batch normalization, which stabilizes training, and an ReLU activation function, which is used to introduce non-linearity and to drop out to prevent overfitting of the model. And then the final output, this of the output layer, predicts the probability for each word in our vocabulary, and we then use the argmax operation to select the most likely word to generate the response step by step instructions. This entire model is trained using a cross entropy loss, which measures the difference between the model's predictions and the actual target words, which are then optimized using an Adam optimizer. Then the user is able to get a fast response, accurate and a fast response. Our third module is a vision transformer, or call it the VIT for image stroke ingredient recognition. So unlike traditional CNNs, a VIT treats an image as a sequence of text. The input image is first broken down into a grid of smaller patches, whereby each patch is flattened and nearly projected to create a patch embeddings. So then the sequence of vectors is fed into a standard transformer encoder, as you can see from the architecture, which is composed of 12 layers. Then the core transformer is the multi-head attention mechanism. This allows the models to weigh the importance of all other patches when processing a single patch, covering both the local and the global relationships between images. After it passing through all the 12 layers as mentioned earlier, a special classification head, this one as we see down here, takes the final processed output and maps it to one into one of the 40 food classes as we saw earlier. So mathematically for the VIT model architecture, as we can see here, there is the classification, which uses the softmax equation, then the training, which uses the Adam optimizer, where the theta is equal to WE and uses a cross entropy for training, as we mentioned earlier. Then there is a gradient flow. Mm. Then for each of the 40 class implementation, it will create embeddings and encode for all the 12 layers. And the mathematical formulation, the complete mathematical formulation, which is equal to logic, logit is equal to the W times W classifier times the H, as we can see there, whereby these are the final tokens that are taken in, and the VIT can continue to process as mentioned earlier. So this is an EDA result output, and as you can see, the blue line is a training accuracy, which keeps increasing as the valuation accuracy is linearly the same. And this happens when the model is memorizing the training data instead of learning new and general patterns. This was first because of the noisy data that we had, whereby some food classes had a few of food items in them, yet the others there was a lot of class imbalance in there. So that made the model to overfit. Looking at the class-wise performance, the model does very well on some classes, achieving a perfect F1 scores, but struggles with the rest. So overall, our Vision Transformer achieved a fine accuracy of 69.7%, while the fine-tuned LLM achieved 56.7%, and the KG-Link prediction model achieved 55.5%. While these numbers show promise, they also highlight that the data scarcity was our biggest challenge. For initial deployment, we selected our LLM model. The primary reason as to why we did this is because it was technique and it was user centered. The LLM has the lowest computational complexity and it's faster, which makes it very easier and responsive conversational experience and also works in resource constrained devices. So and so much more. That was the specific reason. So here is a demonstration of our deployed product, which is the Fumba assistant. As you can see, there, I can select a local recipe like belled mato. Okay, then the system displays the required ingredients and provides a clear step-by-step cooking instructions with predictions, substitution of ingredients, and which a user can navigate through according to the time they have for meal preparation. As with this research project, we faced very many issues. Number one, there was limited access to diverse Ugandan food data, and our RGCN model currently cannot discover new foods. It only is static. And then the computational capabilities of Colab and Cargo are very limited, or other environments are very limited. There was, especially during deployment, there was a problem of computation being expensive. So in conclusion, we successfully integrated our LLM here to integrate computer vision and the KG into a functional multimodal assistant. And the future work, we shall focus more on data expansion and real-time marketing of the data, like getting the prices of the food items and get expand the LLM's language support because it wasn't supporting the Luganda and the local languages. And in conclusion, we'd love to thank Mr. Galiwango for being a very big help to us and all the people that availed themselves to tell us more about the recipe during data collection. We acknowledge their help and thank you so much for listening.